Hello students, I welcome you on behalf of Shri Jayendra Rangzone classes. In previous class, we have seen the refraction of light, the apparent depth concept, and total internal reflection concept and its application. In today's lecture, we are going to study about the refraction at spherical surfaces, refraction by lens, lens makers formula, etc. So let us begin. Let us understand how refraction at spherical surfaces occur. Till now we have applied the Snell's law to the flat surface. Now we are going to study the refraction at spherical surface. Consider an object O on the principal axis of spherical surface. Here the spherical surface is convex. C is the center of curvature. R is the radius of curvature and I is the image. Distance between the optical center or the spherical surface and object is object distance U. Distance between image and spherical surface is image distance V. Now, the rays are incident from a medium of refractive index N1 to another of refractive index N2. From the figure, for small angles, we can write tan alpha nearly equals to alpha, tan beta nearly equals to beta, and tan gamma nearly equals to gamma. Here, tan alpha can be written as mn divided by om. This is right angle triangle. So it can be written, tan alpha can be written as mn upon om. Tan beta for this angle triangle, tan beta can be written as mn upon mc. Same way, tan gamma can be written as mn upon mi. Now, the angle I is the exterior angle for triangle ONC. So for triangle ONC, we can write I is equals to alpha plus beta. Same way, for triangle NCI, we can write R plus gamma is equals to beta. So R can be written as beta minus gamma. Now, at the point of incidence, we will apply Snell's law. So by Snell's law, N1 sine I is equal to N2 sine R. For small angles, we can write sine I is nearly equal to I and sine R is nearly equal to R. So our equation will be written as N1 I is equals to N2 R. But I is alpha plus beta and R is beta minus gamma. So N1 into alpha plus beta is equal to N2 into beta minus R. Putting the value of alpha and beta, alpha is mn divided by om and beta is mn divided by mc is equal to n2. Again, beta is mn divided by mc minus gamma, that is mn divided by mi. Taking mn common from both the sides, it will get cancelled out. So n1 upon 1 upon om plus 1 upon mc is equal to n2 into 1 upon mc minus 1 upon mi. Multiplying inside n1 by om plus n2 by mi is equal to n2 minus n1 divided by mc. Let's say this is equation 1. Now, from this figure, we can see that OM is minus U, taking the sign consideration. MI is plus V and MC is plus R. So put the values in equation 1. We can write N1 divided by minus U plus N2 divided by V is equals to N2 minus N1 divided by R. Rearranging the equation, we will get N2 by V minus N1 by U is equals to N2 minus N1 divided by R. So this is the formula for refraction at spherical surface. This is the relation between object and image distances in terms of refractive index of the mediums and radius of curvature. It holds good for any curved or spherical surface. Now, if we combine two spherical surfaces, the combination is called lens. There are basically two types of lens based on the property or based on the effect that they provide to the light. First are converging lenses which converge the lights, and second are the diverging lenses which diverge the light. The converging lenses are in general called as convex lenses because their surface is bulged out, curved surface is bulged out, and diverging lenses are called concave lenses as their converging surfaces are bulged in. There are four types of convex lens and four types of concave lens. One is biconvex lens. In biconvex lens, it has two convex surfaces. Radius of them may or may not be same. Let's say one radius of curvature is R1 and another surface has radius of curvature R2. If both curved surfaces have same radius of curvature, then it is called equiconvex lens. If one surface is plane and another surface is convex, then it is called plano-convex lens. If one surface is convex and second surface is concave, then it is called convexo-concave lens. Same about the concave lenses. If we have two concave surfaces, but radius of curvature of them may or may not same, then it is called biconcave lens. If their radius of curvatures are same, then it is called equiconvex lens. If one surface is plane and another surface is concave, then it is called plano-concave lens. If one is concave and another is convex, then it is called convevo-convex. As long as our syllabus is concerned, we will mostly deal with biconvex, equiconvex, plano-convex, biconcave, equiconcave, and plano-concave lenses. Now, as we have seen the laws of image formation by mirror, same way we can find the laws of image formation by lenses. First of all, let us understand some basic terminologies regarding lens. The center of lens is called optical center O. O is the optical center. The focus of first surface is F1 and 2F1. Distance between O and 2F1 is the radius of curvature R1. Same way for second surface, focus is F2 and center of curvature is 2F2. So distance between 2F2 and O is radius of curvature R2. O is optical center and all the distance are measured from O. Now let us first see the image formation by laws of image formation by convex lens. Convex lens convex lens converges the light. If light ray is coming parallel to principal axis, then after refraction, it will pass from focus. The reverse of this is if light ray is incident from focus, then after refraction, it will become parallel to principal axis. And if light ray is incident from optical center, then it will go undeviated. There will be no bending of light if it passes from optical center. Same way we can check it for concave lens also. If light ray is coming parallel to principal axis, then after refraction, it will appear to pass from focus. If light ray appears to pass from focus, then after refraction, it will become parallel to principal axis. And if light ray is passed from optical center, it will go undeviated. It will move undeviated. So these are the laws of image formation by lenses. We can use it to form image of an object placed at any position in front of any lens. Now let us see the image formation cases by convex lens. We will put object on different position, and for that how image is formed and where it is formed, that we will check. First, object is placed at infinity. Let's say light rays are coming parallel to the principal axis. Then after refraction, they will pass from focus. As the refracted rays are intersecting, actually the image formed is real. It is formed at F2 and highly diminished. As the image is real, it will be inverted. Now, gradually, we will move the object towards the lens. In the second case, we have kept an object beyond 2F2. We will incident two light rays. One is parallel to principal axis. After refraction, it will pass from focus. And another is passing from optical center of the lens. It will go undeviated. These two refracted light rays intersect at a point between F1 and 2F1. So at this point, image of AB is created, that is A dash, B dash. So if object is kept beyond 2f2. Its image is formed between f1 and 2f1. Again, the image is real, inverted, and it is diminished. Now again we are moving the object near the lens. Now object is placed at 2f2. One light ray is incident parallel to principal axis. After refraction, it will pass from focus. Another light ray is incident from optical center. After refraction, it will go undeviated. These two refracted light rays will intersect each other at point 2f1. So the image is created at 2f1, that is A dash, B dash. Here again, the image formed is real, inverted, and of same size. So if object is placed at 2f2, image is created at 2f1. Again, we have moved the object nearer to lens and we have kept it between f2 and 2f2. So object is placed between f2 and 2f2. Light rays incident parallel to principal axis. After refraction, it will pass from focus f1. Another light ray is incident from optical center. After refraction, it will move it will go undeviated. These two refracted rays will intersect each other beyond 2f1. So image A dash B dash is created. So image is beyond 2f1. It is real, inverted, and of size enlarged. Now, if we keep the object on focus, object is kept on focus. Light rays incident parallel to principal axis. After refraction, it will pass from focus f1. Another light ray is passed from optical center. It will go undeviated. These two light rays, refracted light rays, are parallel to each other. So they will intersect each other at infinity. So if object is kept at f2, image is formed at infinity. Image is real, inverted, and highly enlarged. In the last case, if we keep the object between optical center and focus, we are incidenting ray parallel to principal axis. After refraction, it will pass from focus f1. Another light ray is passed from optical center O. These two refracted light rays are diverging. Diverging rays will not intersect, so we will extend them to the back side. The point where these two extended rays intersect, the image of object AB is formed, that is A dash B dash. So if object is kept between F and O, then image is formed on the same side as that of object. So image is virtual. We can see from this cases, as we keep moving the object towards the lens, the size of image will keep increasing. The convex lens can form both real and virtual images. And virtual image formed by convex lens is always enlarged. Now let us see the cases of image formation by concave lens. This is optical center O, principal axis, focus F1, 2F1, F2 and 2F2. In first case, object is at infinity. So light rays are coming parallel to principal axis. They will diverge after passing from concave lens. This diverging rays will not actually intersect each other, so we will extend them. They will intersect each other at F1. So image is created focus. Here, as the extended rays are intersecting each other, image is virtual. Virtual image is always erect and it is highly diminished. In the second case, if we have kept object at any finite distance from lens, object AB is kept at any finite distance, one light ray is passing from principal axis, it will diverge and appear to pass from focus. Another light ray is passed from optical center, it will also diverge. These two extended rays will intersect each other at a point and image is created A dash B dash. Again here image is virtual, erect and diminished. So the image formed by convex lens can be real or virtual. The virtual image form is always enlarged. Image formed by concave lens is always virtual and it is always diminished. Now, let us see the lens maker's formula. When refraction at two surfaces are occurring, we can say refraction by lens has occurred. One is surface S1 and another is surface S2. Due to it, the refraction has occurred We want to find the final position of image due to refraction by both the surfaces. So in case of image formed by lens, it is in terms of two steps. The first refracting surface forms the image I1 of object O. This is surface 1. Object O is kept in front of surface 1. So it forms image I1. The image I1 will act as object for second surface. Here second surface is shown. Object I1 and its final image is created I. For the first surface ABC, we can write for first surface ABC, we can write N1 upon OB plus N2 upon BI1 is equals to N2 minus N1 upon BC1. This is the equation we have derived from refraction by spherical surfaces. Now, for second surface, we can write N2 upon minus DI1 plus N1 upon DI is equals to N2 minus N1 upon DC2. If we consider thin lens, then BI1 is nearly equal to DI1. So we can write N1 upon OB plus N1 upon DI. We are adding equation 1 and 2. So this two terms will get cancelled out and resultant will get N2 minus N1 into 1 upon BC1 plus 1 upon DC2. This is equation 3. Now, by using the sign convention, we can write OB is equals to minus U, DI is equals to V, and BC1 is equals to R1, BC2 is equals to R2. So our equation will become N1 upon minus U plus N1 upon V is equals to N2 minus N1 into 1 upon R1 minus 1 upon R2. We can take N1 common. So 1 upon V minus 1 upon U is equals to N2 upon N1 minus 1 into 1 upon R1 minus 1 upon R2. If object is at infinity, this is called Lensmaker's formula. If we take object at infinity, then image will be created at focus. So 1 by f minus 1 upon infinity is equals to n2 by n1 minus 1 upon into 1 minus r1 minus 1 upon r2. This is equation 4 and this is equation 5. Comparing 4 and 5, we can also write 1 by f is equals to 1 by v minus 1 by u. This is the lens formula for thin lenses. And this is called lens maker's formula is 2. From lens maker's formula, we can see that focal length of the lens is just not dependent on the radius of curvatures of the surface, but it also depends on the refractive index of medium as well as refractive index of material of lens. If we keep lens in different mediums, then its behavior may change. It may behave as converging or diverging lenses. So let us see how that works. From lens maker's formula, we can write 1 by f is equals to n2 by n1 minus 1 into 1 upon r1 minus 1 upon r2. If lens is placed in a medium of refractive index greater than air, and glass is the refractive index of material such that refractive index of medium is greater than refractive index of glass. So if it is placed in a medium of refractive index N2, which is greater than the refractive index of glass, then nature of lens will not change. Refractive index of glass, that is refractive index of medium 1. If N2 is greater than N1, then this ratio N2 by N1 is greater than 1. So the focal length formula will remain same, N2 by N1 minus 1 into 1 upon R1 minus 1 upon R2. So the nature of the lens will not change. The meaning of this, that nature will not change, is that if it is behaving like diverging lens in air, it will also behave like diverging lens in given medium. But if N2 is less than N1, then N2 by N1 will be less than 1. So N2 by N1 minus 1 will be less than 0. In this situation, the nature of lens will change. That is, if lens is behaving like converging lens in air, it will behave as diverging lens in given medium. So this is the effect of mediums on lens. Now let us understand what is power of lens. It is the measure of converging or diverging capability of a lens. Power is denoted by capital P. It is the reciprocal of focal length. Its SI unit is meter inverse and it is called diopter, capital D. But usually in practical life, we see focal length in centimeter. So P can be written as 1 upon focal length if it is in meter diopter, or it will be 100 upon focal length, which is in centimeter diopter. Now, what will happen if two or more lenses are combined? Consider two thin lenses A and B of focal lengths f1 and f2 placed in contact with each other. O is the object placed beyond the focus of first lens. Now, the first lens produces an image I1. This image is real. It behaves as an object for second lens, producing the final image I. So, for image formed by lens A, we can write 1 upon V1 minus 1 upon U is equals to 1 upon F1. Same way for image formed by lens V, we can write 1 upon V minus 1 upon V1 is equals to 1 upon F2. Now adding this to equation, we will get 1 upon V minus 1 upon U is equals to 1 upon F1 plus 1 upon F2. But 1 upon V minus 1 upon U can be written as 1 upon F is equals to 1 upon F1 plus 1 upon F2. If two lenses are placed in contact with each other, then the equivalent focal length is given by this formula. 1 upon F is the power of equivalent lengths that can be written as P1 plus P2. Now, what will happen if we cut the lenses? We can cut the lenses in two ways. One, vertically. So, cutting the lens perpendicular to principal axis. One is this way. In this case, we will have two lenses, two plano-convex lens. As curvature is changed, their focal length is also changed. If combined lens has focal length f, then these two individual lenses will have focal length 2f. Here, as the aperture means the size of lens is not changing, the intensity of image will remain same. Now, in the second case, if we cut the lenses parallel to principal axis, cutting the lens parallel to principal axis, we will get two lengths in this way, in this manner. Here, the curvature is not changed, so focal length of individual lens will not change, but size of the lens is changed. So intensity of image formed will change. Now, what will happen if we have silvered any side of the lens? Let us see the effects. If lens is silvered from any one side, then it will behave as mirror. We can have multiple cases of silvering of lens based on whether it is biconvex lens or plano-convex or biconcave or plano-concave lens. So if any one side of lens is silver, then the effective focal length of the resulting mirror will be 1 upon Fe is equals to minus 2 upon Fl plus 1 upon Fm. Here Fm is the focal length of silvered side and Fl is the focal length of refracting side. If plane surface is mirrored, then Fm will be equal to infinity because the focal length of plane mirror is infinity. So in that situation, 1 upon Fe will be equal to minus 2 by Fl. So effective focal length will be minus of Fl by 2. Here this negative sign denotes that the nature of lens and mirror will be reversed. Plano-concave lens if silvered will behave as convex mirror and plano-convex lens if silvered will behave as concave mirror. It is solve some questions based on the concept that we have studied. A ball is dropped from height of 20 meter above the surface of water in lake. The refractive index of water is 4 by 3. A fish inside the lake in the line of fall of ball looking at ball at an instant when ball is at 12.8 meter above the surface of water, the fish sees the speed of ball as. Here, ball is dropped from 20-meter height above the surface of water and fish is inside the lake. Let us assume it is just below the surface. When position of ball is at 12.8 meter the water surface, we want to find the velocity of ball with respect to fish. First, we will find the velocity of ball at this position. It has traveled the distance 20 minus 12.8, that is 7.2 meter. So its velocity can be found as vv square is equals to initial velocity is 0 plus 2 into 9.8 into s, that is 7.2. Its square root will give us the value approximately 11.87 meter per second. This is the speed of ball as seen by the observer, which is outside the water. Now our observer is inside the water. So velocity of ball with respect to fish will be first of all, we can write the position of ball with respect to fish. So position of ball with respect to fish will be equal to refractive index of air with respect to water into 12.8 or into position of ball y. So velocity of ball with respect to fish will be equal to velocity of ball. VBF is equal to 3 by 4 into 11.87. This will give us the answer approximately 9 meter per second. This will come 8.9. So we can approximately take it as 9 meter per second. So velocity of ball with respect to fish will be 9 meter per second. In this question, it is given that a biconvex lens is formed with two thin plano-convex lenses as shown in the figure. Refractive index N of the first lens is 1.5 and that of second lens is 1.2. Both the curved surfaces are of same radius of curvature 14 centimeter. For this biconvex lens, for an object distance 40 centimeter, the image distance will be. Here the figure is given in this way. The first lens has refractive index of 1.5 and the second lens has refractive index of 1.2. Both have radius of curvature same, that is 14 centimeter. Now we can apply first lens formula to lens 1. So 1 upon f1 is equals to n2 by n1 minus 1 into 1 upon r1 minus 1 upon r2. So 1 upon f1 is equals to 1.5 minus 1 by 14 minus 0 because second surface is plane. So we will get 1 upon f1 is equals to 0.5 divided by 14. Same way for length 2. We can write 1 upon f2 is equals to 1.5 minus 1 into, it has refractive index of 1.2, so 1.2 minus 1 into 0 minus of 1 by 14, taking the sign convention in consideration. So 1 by f2 will be equal to 0.2 divided by 14. Now, for the combination of lengths, we can write 1 by f is equals to 1 by f1 plus 1 by f2, that is 0.5 divided by 14 minus plus 0.2 divided by 14, that is 0.7 divided by 14. Now, using the length formula, f is 1 by f is equals to 1 by v minus 1 by u. 1 by f is 0.7 divided by 14. We want to find minus object distance is 40 centimeter. Simplify this, we will get v is equals to 40 centimeter. Next question. This question was asked in NEET 2019. An equiconvex lens has power P. It is cut into two symmetrical halves by a plane containing the principal axis. The power of one part will be. It is the equiconvex lens. So both the surfaces have same radius of curvature and same focal length. It is cut into two symmetrical halves by a plane containing the principal axis. That means it is cut in this manner. Both the lenses have same curvature as before, so that focal lengths are not changed. So power will also be same. So power will be P only. This question was asked in NEET 2019 again. A double convex lens has focal length 25 centimeter. The radius of curvature of one of the surface is double of the other. Find the radii if refractive index of material of lens is 1.5. The focal length is given 25 centimeter. It is given that radius of curvature of one of the surface is double than the other. Let's say R1 is equals to R, then R2 will be equal to 2R. Refractive index is given 1.5. We want to find the radii. We can use again lens maker's formula. 1 by F is equals to 1.5 minus 1 into 1 upon R minus of 1 upon 2R. Focal length is given 25 centimeter is equal to 0.5 into 3 by 2R. So 1 by 25 is equals to 3 by 4R. Put the value R, we will get as 8.75 centimeter. So radius of curvature of one side will be 18.75 centimeter and of Another side, it will be 2r. It is double of one side. That is 37.5 centimeter. Let us see the next question. This question was asked in NEET 2019. Two similar thin equiconvex lenses of focal length f each are kept coaxially in contact with each other such that the focal length of combination is f1. When the space between the two lenses is filled with glycerine, which has the same refractive index 1.5 as that of glass, then the equivalent focal length is f2. What is the ratio of f1 is to f2? Here, two thin equiconvex lenses are placed in contact with each other. Both have focal length f. In this situation, the equivalent focal length is f1. So we can write 1 upon f1 is equals to 1 by f plus 1 by f. So 1 upon f1 is equals to 2 by f. f1 is equals to f by 2. Now, when glycerin is filled in the space between these two lenses, it will behave as, we can see this as, one is convex lens of focal length f, in between concave lens of same focal length f but negative, and third is convex lens again of focal length f. So there will be three lenses in contact. So equivalent focal length will be 1 by f minus 1 by f plus 1 by f. So f2 will be equal to f. Taking the ratio f1 by f2, it will be equal to 1 by 2. So 1 is to 2 is the correct answer. The next question, it was asked in NEET 2016. Two identical glass equiconvex lenses of focal length f each are kept in contact. The space between the two lenses is filled with water. What is the focal length of the combination? The question is of same method. You can pause the video and try it by yourself, and then afterwards come again and see the solution. So two equiconvex lenses and space between them is filled with water. So finally we will have three lenses in contact, two convex and one concave. Here, as the refractive indices of convex and concave are different, their focal lengths will be different. Focal length of convex is f. So we can write by using Lensmaker's formula, 1 by f is equals to refractive index 1.5 minus 1 into 1 upon r plus 1 upon r. That is 1 by f is equals to 0.5 divided by r by 2. So we can write f is equals to r. Now, for concave lens, let's say focal length is f dash. So we can write 1 upon f dash is equals to 1.33 or 4 by 3 minus 1 into minus of 1 by r minus of 1 by r. So 1 upon f1 is equals to 1 by 3 into minus of 2 by r. But r can be replaced by f. So 1 upon f1 is equals to minus of 2 by 3 f. Power of combination or focal length of combination is, let's say, capital F. That can be written as 1 upon f plus 1 upon f minus 1 upon f1. So 1 by f plus 1 by f minus 2 by 3f. That after solving this, we will get the answer. 1 by f is equals to 4f by 3. 4 by 3f. So focal length of the combination will be 3f by 4. So fourth option is correct. Next question. This was asked in NEET 2016 again. An air bubble in a glass slab with refractive index 1.5 is 5 centimeter deep when viewed from one surface and 3 centimeter deep when viewed from the opposite face. What is the thickness of the slab? Here we have to keep one thing in mind, that these are the apparent depths and not the real depths. Let's say this is the glass slab and this is the spot. This much is the apparent depth from one side. Let's say it is x. Total length of glass slab is L. Then this depth will be L minus x. As seen from one side, apparent depth is 5 centimeter, and from other side, apparent depth is 3 centimeter. So total apparent depth is 5 plus 3, that is 8 centimeter. Now we can write apparent depth is equals to real depth upon refractive index of glass. So real depth is 8 into 4 by 3 3 by 2, sorry, that is 12 centimeter. So real length of glass slab is 12 centimeter. Next, this question was asked in EIPMT 2012. A rod of length 10 centimeter lies along the principal axis of a concave mirror of focal length 10 centimeter in such a way that its end is closer to pole is 20 centimeter away from the mirror. The length of image is. There is one concave mirror of focal length 10 centimeter. This is pole and this is focus. This distance is 10 centimeter. Its end closer to the pole is 20 centimeter away from the mirror. This is center of curvature. This much distance is 20 centimeter and this is rod of length 10 centimeter. To find the length of image, we will find the position of image of two ends of the rod. Let's say this is end 1 and this is end 2. As one end is on center of curvature, its image will also be formed at center of curvature only. So V1 is 20 centimeter only. Now we want to find V2. U2 is the second end of rod is located at 20 plus 10, that is 30 centimeter, and it is object distance, so it is negative. Focal length is 10 centimeter. For concave, focal length is negative, so F is equals to minus 10 centimeter. We can use mirror formula. 1 by F is equals to 1 by V plus 1 by U. So 1 by V2 will be equal to 1 by F minus 1 by U. 1 by V2 will be equal to minus of 1 by 10 plus 1 by 30. Minus 3 plus 1 divided by 30. So V2 will be equal to minus 15 centimeter. So at this point, V2 is created. This distance will be 15 centimeters. So total length of image will be equal to V1 minus V2. That is 20 minus 15, which will give us the answer 5 centimeters. That is all for today. Thank you.